In this lecture, we prove the most important theorem on discrete valuation rings. So we start with a discrete valuation ring, and we have shown that if you start with a discrete valuation ring, it becomes a PID, a principal ideal domain, and therefore it is Noetherian. It is integrally closed, and integrally closed ring is normal, and it has a unique non-zero maximal ideal M, which is generated by the uniformizing parameter. So this we know. Now we want to work in the opposite direction. So we are given R is Noetherian, normal, and has a unique non-zero maximal ideal M. So this M is not equal to 0, and then it will be a DVR, or discrete valuation ring. So what we have to essentially show is that M is actually a principal ideal, that it is generated by a single element pi. So we want to show that M is generated like this, and then we will get a DVR. So this will be a long theorem, and therefore we will state some facts which we will use. Once we state the facts, it will be easier. Now you should immediately see that this is an example of a Dedekind domain. So this is a Dedekind domain because it is Noetherian, normal, and it has a single ideal. So DVR is a special case of a Dedekind domain. So it is a Dedekind domain with a single ideal. So now let us prove this part, because this has been done before. So for this part, let us first state the facts which we are going to use in the proof. So the first fact is about Nakayama's lemma. So if you have M square is equal to M, that would imply that M is 0. Second thing we want to introduce is associated primes. So consider an R module M, and say there is an element M in M. So annihilator of this M is an ideal, so which is precisely elements of the ring R, which when multiplied by M give you 0. So they kill M. So if you multiply M by elements of R which give you 0, that gives you this thing called annihilator of M, and this is an ideal. So once we have the definition of annihilator, we can talk about associated prime. So an associated prime, also called an assassin of R module M, so this is an R module M, is a prime ideal. So associated prime, that's why we call it prime, because it's a prime ideal of this ring R if there is a non-zero M with the prime ideal precisely being the annihilator of M. So here we said that annihilator of M is an ideal, and this ideal, if it is a prime ideal of ring R, then it becomes an associated ideal of this module M. So essentially it is an ideal whose elements kill the module M. So a fact about associated primes is, so if R is a Noetherian ring and M is an R module, then M is 0 if and only if associated modules, this associated primes of M, are null set. So in other words, what we are trying to say is that if M is non-zero, then there has to be some non-zero element which is lying in the associated prime of M, and this is the fact which we are going to use. We are going to take M as non-zero, and we will say that there actually exists a non-zero assassin of the module M. So we are saying there is a non-zero assassin, non-zero assassin. So this fact we are going to use for the proof. And finally we talk about integral element. So consider this ideal M. So M is an ideal, so you consider it as a finite R module with some Zm lying within M. Then Z is integral over R. So this is another fact about integral elements. So put it as fact number 3. So then Z is integral over R. So this is the fact. Now if R is integrally closed, in our case R is integrally closed because it is normal, and normal means integrally closed, then that would mean that Z lies in R. So let us start proving the theorem. So set K as the field of fractions of our ring R. So step 1. So we know that we have a non-zero maximal ideal. So we can use contrapositive of this statement. So if M is not 0, then M square is not equal to M. So we are using the contrapositive. So we have m is not equal to m square precisely because our m is not 0. We have non-zero maximal ideal and we are going in this direction. We assume this is true. So we have to show that m is generated by a single element. So we choose some element x which lies in m minus m square. So we have to show that m is generated by this element x. So we are going to proceed by contradiction. So what we are going to say is that suppose there is an inequality here. So this is not equal and x is lying within m. So you can always consider a module m which is m modulo the ideal generated by x. And this module is non-zero precisely because we are saying that these two are not equal. So m is non-zero. So now you come here. If m is non-zero, if and only if this associated primes of m are not 0. So if and only if associated primes of m are not 0. So that means there exists some y in m minus x. So here it is m modulo x, here it is m minus x, such that this y serves as an assassin of m. So that is that y will kill the elements, make them 0. So making them 0 means what? You have making them 0 here means that they have to come and lie in this ideal x. So we have my lies within ideal x precisely because this is non-zero. So this is our step 1. So we are choosing y which is in ideal m but not in the ideal x. And the contradiction is going to be that we will end up getting y is in the ideal x. This is the contradiction, and that is precisely because to start with we said that this is not 0 because m is not equal to x. So we have to go from here to this last line here. So first notice that 1 by x is not lying in the ring R precisely because x lies in the maximal ideal m, and it has to be a non-unit. Otherwise you will multiply it by 1 by x and get 1 lying in the ideal m, which will not make m an ideal anymore. So it will not be a proper ideal anymore. So it has to be the case that 1 by x does not lie in the ring R. So therefore if you multiply it by y, this y by x is a fraction. It does not lie in R, but it will lie in the field of fractions of R. So it lies in the field of fractions. Now x lies within this ideal m because it is m minus m square. So if you take y by x times m, then the denominator will just cancel out and you will still lie in the ring R. So there are two cases. We are going to show that the equality is not possible. So it has to be the case that y by x m lies strictly within R. So what if y by x m is equal to R? So this would mean that there is a y prime in m. So this equals to R means that it has to generate 1. So that would mean that there is some y prime that you can say that y prime y over x is 1, or x is equal to y prime. Now y we chose as element of m. Y prime is also an element of m. So x equals to y prime means that x is an element of m square because this is an element of m and this is an element of m. So x is an element of m square, and this is a contradiction precisely because we are saying x lies in m but not in m square. It is m minus m square. So this case is not possible. So the only case possible is that y by x m, this lies within R. But this is an ideal in R. So this is an ideal precisely because x lies within m and it is going to cancel with the denominator. So this will become an ideal in R, but there is only one ideal here. So spec of R is precisely equal to 0 and m. So it has to lie within the maximal ideal m. So this will lie within the maximal ideal m. So put this y by x as z. So we get zm lies within m. And now we use here. So zm lies within n. That means z lies within R because R is normal. Or you can say y by x lies in R. Now you already have the contradiction. Here we said y by x is not in R. Here we are saying y by x is in R. But bring it here. So if y by x is in R, 1 by x is already not in R. So the only way this can be in R is if y lies within the ideal x, and that is a contradiction. So thus we have been able to show that if R is Noetherian, normal, and has a unique non-zero maximal ideal M, then it is a DVR. And in addition, we have been able to show that, since this condition characterizes a discrete valuation ring, and this is a Dedekind domain because it looks like this: spec of R is 0 and M, and R is Noetherian and normal. So therefore this becomes a Dedekind domain. So discrete valuation rings are one of the most important examples of Dedekind domains, and another example is this ring of integers like this.